So today I want to give you a bit of a light introduction of this AI in the materials industry using some of the case studies from our online course of the same name, which I hope then might inspire you to use some of these techniques for your own applications, even if they're not materials related. So let's get started. Now, the reason why we're so interested in artificial intelligence in the materials industry is because we've entered the era of Industry 4.0, where most machines in our factories actually have many sensors which are interconnected. This means we can gather quite a lot of data very quickly, but this of course becomes problematic then to interpret, as of course humans can't really process terabytes of information. So this is why we need artificial intelligence. So what is artificial intelligence? Kenneth already gave a nice introduction, but how I'm going to define it here is basically as a series of techniques that allows you to extract information from data and then use that information to make predictions. And it's very important here that we talk about information. As imagine, for instance, we have a big data set on one single material, then it's unlikely we're going to be able to predict anything for another type of material. Whereas as we have the same amount of data for 100 different materials, then it's much more likely that we'll be able to say something about a new material. As this, of course, might then be similar to one of those other 100 materials we've already seen. So this is something to keep in mind, that you need a lot of variation within your data set. So now let's talk a bit about the types of AI. So if we have small data sets, we typically go to what we call classical machine learning or even statistics, where some of the techniques even overlap. But a big difference is the nuance. So statistics focuses more on trying to get human interpretable insights from your data, whereas machine learning really cares most about making predictions for new data sets, and thus the performance that you have on these new data sets, where interpretation is nice, but it's not your main concern. Now, in both cases, you kind of need to translate this raw data to make it more interpretable for the machine learning, because there's not that much data. And this can, of course, be a little bit tedious. So this is why deep learning has become so popular, as Kenneth showed, because it can actually extract insights from raw data like images without us having to pre-process it a lot. And this, of course, requires the use of GPU, where these old methods typically start having issues when you have a lot of data, simply because they go out of memory on your standard CPU nodes. But we do have, of course, big memory nodes on the Hpc. All right. It's important, of course, that deep learning then becomes a bit more difficult to interpret, though we're going to get back to some interpretation methods later. So like I said, we'll look at a few of our case studies from our course. So what do we have there? We first have two applications on steel. It's actually the same application, detecting defects, but from two different viewpoints. One where we use spreadsheet data, so your typical Excels as our starting point, and another where we use deep learning on raw images. Then we have a different type of application on glass. We're trying to discover one specific optimal type of glass among a large search space. So this is kind of a search problem. The final one tries to simplify sensor data, but I won't go into detail on that today. Because these three nicely show you a CPU, GPU, and a cloud application. So let's have a look at these case studies. So what is a steel plate defect? Well, you see a few here. Easiest to interpret is like a scratch or a pit in the surface. You don't want your car to come pre-scratched, let's say. But there are other things like these patches and scratches, cracks on the surface and so on. So you want a nice clean and shiny plate, let's say. So we want to detect this. Now, if we want to do this the old school way with spreadsheets, we of course need to convert these images to the spreadsheets, which can be a little bit troublesome. So this is a multi-stage process. First, we need to detect that there's a defect. You can imagine, you can, for instance, look at the pixel values here. So very bright pixel is clearly different in the defect here compared to the background, which is the plate. So you can just say above a certain threshold, we likely have a defect. But you can imagine that this depends on lighting and so on, so you have to be very careful. Then once we have kind of like isolated this defect, we draw a box around it and cut it out of our camera feed. We want to translate into a spreadsheet for which we use what we call a featureizer. So we want to extract interpretable features, like for instance, the size and shape of this box, the average brightness in the box, and so on. And then finally, we give this spreadsheet data to our machine learning model, which is going to try and classify this defect. It's important here, of course, that we want to use this in production eventually. So we shouldn't only think about the accuracy of our model, but also about the speed and the impact if something goes wrong, which I'll also come back to later. Now, what kind of machine learning model will we use for this? We'll use what's called a decision tree. So let me give you a quick example. Imagine we are deciding how to go to work based on a specific day. Then we could ask ourselves, what's the weather like today? If it rains, we'll take the bus. If it doesn't rain, then we'll ask ourselves how much time we have. If we don't have much time, we'll again take the bus. But if we have a lot of time, then we might walk to work. And here we're kind of classifying our days using both the categorical variable and this continuous variable of time into these two categories. So you can see this is a quite easy to interpret model, and you can actually determine these decision trees automatically. What's also interesting is that you can control the speed, so they typically run on CPU by, for instance, constraining how many decisions you make. So you can trade accuracy and speed. So what does a decision tree look like for instance, classifying a bump? So I'll guide you through this. The first decision we make here is based on the length of the conveyor belt. So you can imagine if a plate is rolling on a conveyor belt, maybe shorter means there's more edges that can get bumped. So that could make sense. But it could also just mean that these machines with a smaller conveyor belt actually are older and are more prone to causing defects or something. So this is something you then have to look at in production. Then we are trying to get to this blue region, which is the bumps. And the second important decision for this is the type of steel. So in this data set, we only had two types of steel, and one is clearly more resistant to bumps than the other. And this then sends us to this third decision, where we are looking at the thickness of the plate, where we can imagine that a thinner plate is much easier to dent and thus cause bumps. And that is indeed this decision that happens. And then we already get quite good classification. So you see, this is quite easy to interpret and actually creates a quite nice decision tree automatically. The problem is that you can make these decision trees infinitely deep. So you can kind of separate each individual point, even if it's just different because of noise or even if it's wrong. So this can kind of cause issues if you then go to new data. And this is what we call overfitting. So we can solve this with a technique called random forests, where we actually use these not very deep trees that are not perfect, but instead of making one, which might be a bit off target, we will make many. And then if you average them, you can imagine that the final result is actually better than each individual one. But for this, it's important that there's a lot of variation in your trees. Otherwise, you will always make the same guess. And of course, your average is not going to improve. So for that, you actually need to induce variation, which we do by varying what we call hyperparameters. These are the parameters that you give to your model to tell it how to determine its own internal parameters. These are things like how many trees do you have, how deep are your trees, how much of your data set do you show each tree, and how many of your columns in your spreadsheet do you show to each of these trees. And there are, of course, many more. One nice thing is that you can optimize this using high throughput screening. So while creating one of these forests might be quite light on CPU if your data set isn't too big, you can then sample many of these different combinations of these hyperparameters to find your best forest quite quickly if you have a lot of CPUs available. Now let's look at some results. So the data set that we used here has many different defects, some scratches, some bumps, this pastry defect, and then some collection of other faults. So that contains basically all the junk in the data set. So it might be a bit more difficult to interpret. And what's important here is that we also have 2 minority classes. So these are quite small. And what's important about this is that if you train a machine learning model and you look purely at the accuracy, then there is some risk that these kind of minorities get lost. And then you have to ask yourself if that's okay, or if you should kind of bias your training procedure to conserve these, if, for instance, they are much more important than a very common defect. If you look at the results, we see in accuracy, we have quite good results, so nearing 100%, where bumps are a little bit less good, and the other faults are the worst, because they are, of course, very diverse. So you can imagine that this is then okay overall, but you see that this 6% error could still include an entire class here. So you have to be careful and also look at other metrics, which, for instance, keep into account false positives and false negatives more than just the pure accuracy. All right. Now, as you saw with these decision trees, we should be able to interpret them quite easily, but because we are inducing all this variation in the forest, we kind of lose that. Luckily, there are explainable AI techniques called SHAP, which work both on random forests and many other models that lets you kind of sort your features by their importance. So this is an example here. If you look at the 5 most important features for the classification of a bump in this case, you see that the squareness is most important. So this is the box around it, basically saying that a bump is kind of round. So if it's very square, it's good. The type of steel and the length of conveyor we already saw. Then there is this parameter, which basically says that bumps are quite small compared to scratches and so on, also very important. And then the final one here is the luminosity, which basically says that bumps are not that bright compared to a scratch, for instance, which is highly reflective. So this makes quite a lot of sense. And then you can ask yourself whether these decisions then match what you would expect as a materials expert, for instance. You can also then retrain your model with, for instance, only these 5 columns, and you would see that you get nearly the same performance, but a much faster model. So this can be quite powerful. All right. So it's quite nice we can actually recover the interpretation. Now, the problem is that we still need to first determine all these columns that we saw on the previous slide. And it would be much nicer, of course, if deep learning could do this for us. And this is exactly what happens. So let me explain the details of the deep learning a bit more based on this example of facial recognition. So here you get the raw pixels as input for your first layer, a layer of neurons, which is effectively just a linear regression with some kind of nonlinear activation function behind it. And then what happens is that it's going to try and make features from this. In the first layer, this can be quite difficult. So what you do is you look at nearby features, going, for instance, from black to white here, you can easily detect an edge. If you have a look at the mouth or the nose, the edge is still detectable, but it's a bit less intense. So you kind of make a map of different kinds of edges with different orientations and different amplitudes. And that you then pass on to the next layer, where you can use it to detect specific shapes like eyes and noses and so on. And eventually you get kind of a smaller and smaller representation containing much more complex information of this image. And then the final part is actually a bit similar to the random forest or to normal linear regression or classification algorithms, where you use these features to then make your final predictions. And you could even use a random forest on these features here if you wanted to, just a bit less efficient. All right. The problem, of course, is that we have many parameters here to create these features, so you need these very big data sets. But there are some ways around this. The most important one is called transfer learning. we can basically do this because companies like Google and Facebook have trained these models on giant data sets with millions of images, thousands of classes. And you can then imagine that the features you produce must be quite generic. Also, we can imagine that there might be some metal texture somewhere in this giant data set, so it should be able to interpret the steel plate. But of course, to detect any specific defects, we'll have to train a bit further, but we can then do this with much less data. This is actually a quite powerful technique, and one of the reasons why we don't usually adapt our image models too much, as then it's more difficult to use transfer learning. All right, so how do you train a neural network? As Kenneth already said, GPU memory here becomes the constraint. So you have to work in batches, since images can be quite big. Imagine, for instance, we have a batch of 4 here and 2 classes. Then we will basically iterate through our data set like this. But the problem is that we might then have batches which have only 1 class. So you kind of have to optimize your batch size so you still have variation and your model won't bias away. So you have to make a trade-off between the size of your image and the number of images you can process, for which these new A100 GPUs will be very valuable, so we can actually use bigger images. All right, there are some other ways to artificially increase your data, an important one of which is data augmentation. So imagine this batch here of 16 images. What we've done here actually is rotate each image a little bit, change the brightness a bit, and perform some other transformations. And this kind of prevents the model from memorizing the original image if it would always see it in the same way. And this is extremely valuable to prevent overfitting. One possible problem, however, is that in some libraries, these augmentations can happen on the CPU, and you need to be very careful if you have a fast GPU that you're not just bottlenecking your calculation on the CPU that happens, operations that happen before each batch. So you should examine how much time this takes, and where necessary, try to find a GPU implementation. Okay, let me now show you some results. So what you see here is the actual predictions, the actual classes versus the predicted classes. And this blue diagonal means we basically get nearly everything right, except these 3% errors for 2 pairs of classes. Now, one important thing is that even if you have good results, you do need to be a bit skeptical, since there are ways things can still go wrong even if your metrics look right. Typically by some kind of data being duplicated between your training data and the thing you're testing on. So be very careful. Luckily, there are also explainable AI techniques for deep learning. So you see here 2 images of a scratch. And we will again use this SHAP technique to tell us which input features are important. And the input features now are just the pixels. So what we see here is that we have exactly the scratch here highlighted, and where it seems to concentrate on the bright patches. So it's a bit more interested in this region than this region. Here it's less bright. So we see it concentrates on the scratch a little bit less, and it also looks in the environment where you do see some kind of light scratches and directionality because the plate is rolling in a specific direction. And it seems to then use this as well in its decision. This makes sense. So it's not unlikely that it's making a good decision. But things don't always go that great. So this is an example here of 5 images where we have something very weird going on. And you see that it's actually concentrating more on the edges and the corners. And this is actually because the data set was made through some kind of a surface scan. So it scanned the surface, and this caused images to be partially overlapping. And if these overlapping images are both in the training set and the sets you test on, then it can actually cheat by just kind of memorizing certain patches in your data. So this is then, of course, very bad if you want to try new data. But it's very nice that we can detect this with this SHAP, because, of course, if it's cheating, it will have a very high accuracy. All right, so this is the end of this application. And now let's have a look at this glass problem. So what we want to do here is find a glass which has a very high refractive index, so it will break light very strongly, for instance, useful in a laser or optical fiber application or something. And we want to kind of make a recipe for this. So which elements do we combine to find a material that makes this kind of glass? And the problem here is that if we make a data set which contains many different materials and then train a machine learning model on it, we will get good performance probably, but we will already have done most of our experiments. We will have wasted a lot of time because we're only looking for one specific material. So we want to bypass this with what we call active learning. In active learning, we link the predictions to the production of the data. So we start with a very bad model, but it tries to guide us to what data it needs to become a better model for our specific goal, finding that material. And then we can produce data either through experiments or through physical simulations on, for instance, a CPU cluster, to try and then optimally improve our model and then gradually iterate till we find what we're looking for. And this can save us a lot of time and money. But the problem is, of course, that we have these interactions and that we need to store our results somewhere. And for this, the VSC cloud, for instance, is very useful because you can then interact both with the CPU clusters and the GPU clusters very quickly to produce and process this data. All right, so let me introduce then how this works for our application. So imagine we have two elements here, A and B. We want to combine them, and so we can create a kind of grid where we start with little a to a lot A and little b to a lot B. And of course, we first need to produce some data as we can't train on no data. And then some of this data might be bad, some mediocre, some might be good. Now, then you can already kind of see that, okay, if we have two bad points close together, it's not unlikely that this entire region is kind of bad. But it's less easy to say that for the good point, as it could get a little bit worse or a little bit better nearby, and the same for the mediocre. And for this, we use then a machine learning model, which kind of outputs an uncertainty together with its prediction. And then it can kind of make a trade-off. So do we want to explore more? Then you look more to uncertain regions, even these unexplored regions, as there might still be better samples there. But if we do not like uncertainty too much, we will immediately go to this good region and just, say, we found something, let's be happy with it. So these kind of trade-offs you can then include in your machine learning itself. All right, let's now look at some results. First, what happens if you randomly search? So you see, if you randomly search, we do immediately find something that's kind of okay. So this is the refractive index and of each of the materials that we look at in order. And if we then keep looking, basically it doesn't improve for a long while. Then at some point, we immediately find the best material in our data set, about 2/3 of the way through. Now, this is, of course, sheer luck. So we could have found it on the first sample, or we could have found it on the last sample. Now, if we use this active learning, we see that we actually immediately find it. Okay, that's because this problem was kind of easy and the data set a bit biased. But what's important is that you actually see that all the samples are kind of ordered. So the average refractive index, as we look at more materials, goes down. And this would let us, for instance, stop our search after like 10% of our data, saving us a lot of CPU compute time or a lot of experimental time. So this is extremely valuable. All right, so that's somewhat the end of this example. Let me now quickly talk about deployment. So once we have these machine learning models, we of course want to use them in production. And then you're going to have to choose between running it on-premise in your factory or in the cloud. On-premise then has the disadvantage that you need to add hardware and you need to maintain it, but it's very close to the data source, so you have low communication, especially if you have intense camera feeds that need to be processed live. It's going to be difficult to send it to the cloud very quickly. But you will be able to interact much slower with the HPC, for instance, meaning active learning would be much more difficult and general R&D. In the cloud, it's of course the opposite. You don't have to manage your own hardware, so you have much higher latency since you need to communicate, and you can do your R&D quickly. So basically, the cloud is best if you want to have like a dashboard to visualize data, run some apps where people, for instance, upload one single image, or store some databases for your R&D, for instance, for active learning. But you really have to look at your data rate and the confidentiality of your data to see what's optimal. Now, to round up, let me summarize what we've learned about HPC and AI. So for small data, we typically use CPU-based implementations that can parallelize either on the data, for instance, different trees with different data, or on the models themselves. So when we do hyperparameter screening. And many classical algorithms actually require quite high memory because they often try to load all the data in memory at once and even interact between each combination of two data points or something. But we do have high data nodes up to like 500 gigabytes or even more on the HPC clusters. So you can get further than you would on your own computers. What's important is, of course, these methods are quite fast, as Kenneth mentioned, which contrasts, of course, with then deep learning, which is often a bit slower, but then higher accuracy. So it really depends on what speed you need in your production. If you then look at big data, we typically go to GPU-based applications, where we need to take a batched approach because we're limited with GPU memory. Though, as we saw with these 800 GPUs, this might actually start solving itself, as we are going from like 16 gigabytes of memory to 40 or even 80, which is an incredible jump. But you need to be careful since your CPU might still be used for pre-processing, and where necessary, you might actually have to fix this up if you really want your full speed. Then inference is always faster than training, so you can make predictions even on the CPU, but it's still going to be slower than your simpler models. So it really depends on the rate of the data that you want to process, whether this is worth it. All right, so that brings me to the end of my presentation. And thanks everyone for listening, and of course our partners for helping us make this course and case studies. We'll now go to Kurt for a more in-depth application in the industry.